Hi everybody. In this session we are going to discuss worksheet questions based on thermal properties of matter. Let us two metal rods A and B, each of length 50 cm, diameter 4 mm, are joined together at temperature 30 degrees. Okay. What is the change in length of the combined rod at 230 degrees centigrade? Given linear expansion quotients of rods A and B are respectively so and so. See here, A is a rod. Let me change the color. A is a rod whose length is 50 centimeter. Two metal rods A and B, each of length 50 centimeters. Even this also 50 centimeters only. This is also. This is B rod. Okay, fine. Diameter 4 mm. Diameter 4 mm. Both are having 4 mm. 4 mm diameter. Okay. Diameter. Next. Initial temperature theta 1 30 degrees. Theta 1 or T1 you can write. No, not a big task. And it is heated to theta 2 is 230 degrees. So temperature difference is 200 degrees. 200 degrees is temperature difference. Next. Linear expansion quotients are given. Alpha of the first one is 2 into 10 to the power of minus 5 for degree Celsius. The other one, alpha B, is equal to, this is for A, 1 into 10 to the power of minus 5. Given linear expansion. What is the change in length? Delta L is equal to L alpha delta theta. L is 50 centimeter, so centimeter, answer will come in centimeter. Alpha value 2 into 10 to the power of minus 5, temperature difference 200. This is for first one. Plus second one, L alpha delta theta, this is for second one, that means B1, this is A1. A1 plus B1, you need to add, that is 50 centimeter into this is 1 into 10 to the power of minus 5 into 200. So you can take common of 50 centimeter, 200 degrees Celsius, 10 to the power of minus 5. So you left with 2 plus 1, right? So 5 2s are 10. 1, 2, 3. 10 to the power of 3 into 10 to the power of minus 5 into 3. Now this is 4 zeros. So 10 to the power of minus 1 into 3. So it will be how much? Delta L is equal to 0.3 centimeter. 0.3 centimeter means just 3 mm. So answer is C. So individual expansions you have to take and you have to add up. That I will write here once again for you. That is delta L of A plus delta L of B. You need to take up individually and you have to add. Hope you understood. Next. In the figure, vacuum, some chamber B and chamber A. In the figure, the chamber A contains a gas, okay, movable chamber B, movable, placed on the top of the gas, and it contains N metal balls. The weight of the chamber B is supported by the gas, chamber C is vacuum. Let the gas be in equilibrium at pressure P. Let P dash be the pressure. If one of the ball is taken away, then P minus P dash by P is. So one of the ball, how many 5 are there? If one is removed, then what is the change in pressure? By the original pressure. What is the change in pressure? By the original pressure. And he is asking N balls are there, not 5. N are there. One ball is removed. So in that aspect, we need to do this problem. Yeah, it can be done like this. See, initially the pressure caused by these balls, that is pressure initial is equal to force or thrust by area. Force is equal to N, each ball of mass M and G, mg by area A. This is initial. Finally is one of that supporting ball is removed. So N minus 1 into mg by A. n minus 1 mg by a, that is p dash. Now he is asking p minus p dash by p. The difference will be, see, this is n bodies, here n minus 1 bodies. So what is the difference? One body only the difference. So mg by a by nmg by a. So on cancellation 1 by n will come. That means option D. Yes. Next, a hole of diameter 5 centimeter into 10 to the power of minus 2. Answer is also in centimeters, so we'll check it out. Next, is drilled in a metal sheet at a sheet at temperature theta 1 is equal to 30 degrees Celsius. The linear expansion of the metal is 2 into 10 to the power of minus 5 per Kelvin. Okay, per Kelvin per degree Celsius same. Diameter of the hole when the temperature is raised to 230 degrees Celsius. Temperature is raised to 230 degrees Celsius. That means temperature difference is equal to 200 degrees Celsius. Yeah, and he is asking the diameter. This is initial diameter you can take. Final diameter is equal to initial diameter of 1 plus alpha delta theta. That is 5 into 1 plus alpha value 2 into 10 to the power of minus 5 into delta theta 200. So that is equal to 5 into 1 plus, here 2 2s are 4 into 10 to the power of minus 3. So 5 plus 5 4s are 20 into 10 to the power of minus 3. So this is 5 plus 2 into 10 to the power of minus 2. That is 5 plus 0 2. Okay, it's in centimeter, so answer will be in centimeter. Yes. So you should be patient enough to do calculations. Okay, don't skip the calculation work. Don't guess, don't predict, just do it and put. Okay, next. Find the ratio of length of a steel rod and copper rod if the steel rod is 4 centimeter longer than the copper rod at any temperature. At every temperature, the difference between the two rods is 4 centimeter. Okay, at any temperature. The quotient of linear expansion for steel and copper is alpha. Quotient of linear expansions. He didn't give a, I think, incomplete question. I'll fill these questions. That means data should be given. Okay, I came back with those data. Let me go to slideshow. Yeah, and yes. So here the quotient of expansions are, one is copper, steel. Okay, steel. Steel is 1.1 into 10 to the power of minus 5 per degree Celsius, and alpha of copper is equal to 1.7 into 10 to the power of minus 5 per degree Celsius. So to have the same length at every temperature, L1 alpha 1 delta theta must be equal to L2 alpha 2 delta theta. That means L1 by L2, that is L of steel by L of copper, is equal to alpha of copper by alpha of steel. So alpha of copper is 1.7 into 10 to the power of minus 5 by 1.1 into 10 to the power of minus 5. So answer will be 17 by 11. 17 by 11 is option A. Yes. Next. The moment of inertia I of uniform rod about a perpendicular bisector increases to I plus delta I. Moment of inertia I became I plus delta I. Okay. Delta I is the increment. Okay. If the temperature is increased by lightly delta T, temperature change is delta theta is equal to delta T. Light change, he said. That means approximations you can use. If the quotient of linear expansion I alpha, linear expansion I alpha, okay, then delta I by I is delta T by T. Assume. I will recheck the statement construction and I'll do. I made the necessary changes. I read the question once again. The moment of inertia I and is changed to I plus delta I. If the temperature is increased lightly to delta T. Quotient of linear expansion, previously it was typed wrong, this is alpha. And then delta I by I is, assume delta T by T is very, very less than 1. So these things are missing, I added, no problem. Now this is going to become, yeah. Here I is equal to moment of inertia of the rod is equal to ml square by 12, ml square by 12. So I dash is equal to m l plus delta l square by 12, and I dash is I plus delta I is equal to m by 12 l plus delta l whole square. So I you take common, 1 plus delta I by I, because I want that only, that's why. That is equal to m by 12 l square you take common, so it will be 1 plus delta l by l square, because square is there, that's why l square will come common. And I and ml square by 12 you can cancel. One more step I can write, 1 plus delta I by I, from binomial expansion 1 plus 2 delta L by L, because small temperature change, and 1 gets cancelled. You got delta I by I is equal to 2 delta L by L. Delta L by L, delta L by L is alpha delta T, alpha delta T. So 2 alpha delta T. How sir? Delta L is equal to L alpha delta T, right? So delta L by L is equal to alpha delta T. So that I brought. So delta I by I is 2 alpha delta T. So this is 2 alpha delta T. Next, the two rods whose lengths are L1 and L2 with heat conductivity quotient K1, K2 are placed end to end. Two rods, one and the other, Two rods are placed end to end. Thermal conductivity is K1 and K2. Lengths are L1 and L2. Wow. The heat conductivity quotients in the uniform rod of L1 plus L2 whose conductivity is same as that of the system is, that means effective thermal conductivity is how much for these two rods whose conductivity, okay, effective conductivity he is asking. So for that we need to take up the rate of conduction. With the help of rate of conduction we can conclude the conclusion. Yeah, from rate of heat transfer we got up R is equal to L by Ka, thermal resistance. Here two are connected in series. So in series R is equal to R1 plus R2. So the series combination total length is L1 plus L2 by effective K, effective A is equal to, this is L1 by K1A plus this is L2 by K2A. So A gets cancelled, and here it is L1 K2 plus L2 K1 by K1 plus, K1 into K2. This is LCM, right? So K1 into K2. K1 into K2, that is equal to L1 plus L2 by K1. Now I want K. So K is equal to L1 plus L2 into K1 K2 by L1 K2 plus L2 K1. So this one comes as first option, numerator okay, denominator K2 L1 K1 L2. First option okay. Yes. Next, the specific heat of helium at constant volume is, specific heat C is equal to 12.6 units. The specific heat of helium at constant pressure is, at constant volume, at constant pressure is in dash approximately. Okay, in this units, what is the value? And R is equal to 8.314. So what is the relation between Cp, Cv and R in moles? So Cp minus Cv is equal to R, and he is asking Cp, that is equal to Cv plus R. Cv value how much? Cv 12.6 into R value how much? 8.314. So 12 plus 8 around 20. So 20 plus something should come. That means 20.9 is there, the option. So that will be the answer. Next, the wavelength of the radiation emitted by a black body is lambda is equal to 1 mm. Then the Wien's constant B is 3 into 2.9. Actually, he gave 3 into 10 to the power of minus 3. Okay, meter Kelvin. Next. Then the temperature of the body is equal to T is equal to how much? Temperature of the body is equal to B by lambda. 3 into 10 to the power of minus 3 by lambda is 1 into 10 to the power of minus 3. So that is equal to 3 Kelvin. So such a small temperature it is. Next. An electric heater with constant heat supply rate is used to convert a certain amount of a liquid ammonia to saturated vapor at high pressure. The heater takes 14 minutes. T1 is equal to 14 minutes. 14 minutes to bring the liquid at 15 degrees Celsius to 50 degrees Celsius. Delta theta equal to 15 degrees Celsius to 50 degrees Celsius. And 92 minutes to convert the liquid at the boiling point to vapor. T2 is equal to 92 minutes to vapor. This is 14 minutes to liquefy. Bring the liquid at, okay, next. If the specific heat capacity of liquid ammonia is P is equal to 4.9 kilojoules per kg Kelvin, and the latent heat of vaporization of ammonia is L is equal to how much? Okay, so total heat produced is equal to the heater, certain heater, oh fine, okay. So heat delta Q is equal to MC delta theta plus ML. This is the total heat liberated or required. This one you have to calculate. Yeah. So this heat only I will calculate separately. That is heat required, rate of heat produced into time T1 is equal to MC delta theta. Similarly, rate of heat produced into T2 is equal to ML. So that on dividing one with other, what happens? RR gets cancelled, MM gets cancelled. So it will be easy for me. So in that sense, what I am going to do is, I am dividing one with other. So T1 by T2 is equal to, we want latent heat, okay, no problem. And C delta theta by L. So L is equal to C delta theta into T2 by T1. Just substitute and you'll get the answer. C value, C specific heat 4.9 into temperature difference 35 into T2 92 minutes, and this one 14 minutes. Both are in minutes only. You can simply cut, and this is 14 will go around 5-6 times, around 1127. It will be a 1000 level. So 1127 kilojoule, because everything in that aspect, kilojoule per kg Kelvin. Next. A slab of stone of area 3600 centimeters square, area A equal to 3600 centimeters square, and thickness T is equal to 10 centimeter, is exposed to the lower surface to steam at theta 1 is equal to 100 degrees Celsius. A block of ice is at 0 degrees Celsius at the upper surface. So here is a slab, here is an ice, and this is at 0 degrees Celsius, and here is 100 degrees Celsius, and this is its area is given, its thickness is given. Then thermal conductivity is equal to, you know, rate of heat transfer 0 degrees, and in 1 hour 4.8 kg of ice is melt. In 1 hour 4.8 kg, time T is equal to 4.8 kg, and what you call 1 hour time equal to 1 hour, and ice melt is equal to delta M is equal to 4.8 kg. So how much heat is transferred? ML by T, heat transferred, that is dq by dt is equal to heat transferred equal to ML by time. M is 4.8 into L value 80 calorie, 80 into 4200. by time t value 1 hour, 60 into 60. This is heat transferred, 60 minutes into 60 seconds. This rate is equal to Ka delta theta by L. So that means 4.8 into 80 into 4200 by 60 into 60 is equal to K into A value. A value 3600 centimeter square 10 power minus 4 into delta theta 100 by length is nothing but thickness 10 centimeter into 10 to the power of minus 2. So on subjecting K value, you are going to get around 1.24 units. So that is K. Yes, next. The change in density of mercury when it is heated from 10 degrees density variation. Okay, theta 1 is equal to 10 degrees Celsius and theta 2 is equal to 60 degrees Celsius, temperature difference 50 degrees Celsius, and the quotient of volume expansion of mercury gamma is equal to 18.2 into 10 to the power of minus 5 in proper units. Okay, then delta change in density we are expecting. So change in density formula delta rho is equal to rho into gamma delta t. Okay, yeah. So here he is asking percentage change, then happy so delta rho by rho is equal to gamma delta t. Gamma delta t is gamma 18.2 into 10 to the power of minus 5 into 50. This is delta rho by rho into 100 will give you percentage change. Percentage change equal to you just into 100. So this is 18.2 into 5. Roughly we are going to have 0.1 closely 1 means B option 0.91%. When a uniform metallic rod rotating about perpendicular bisector with constant angular speed is heated uniformly to raise its temperature lightly, its speed of rotation increases. And when a metal rod is heated uniformly to raise the temperature lightly, its moment of inertia increases. See, moment of inertia increases, that is true, because on heating length increases and on. What about A? When a uniform metallic rod rotating about perpendicular bisector with constant angular speed is heated uniformly, the rise in temperature lightly, the speed of rotation increases. Speed of rotation should decrease, right? Because moment of inertia increases, speed should decrease. So option A wrong, B true. A wrong, B true. Yes. Next. A cylinder of diameter D is equal to 1 centimeter, and at temperature 30 degrees centimeter to be solid into a hole of I think to be placed, okay, to be solid into a hole of diameter D2 is equal to 0.9997. That means it must be heated, okay, in the steel plate at the same temperature. Then minimum required to raise the temperature of the plate is okay. So temperature rise, you need to take up the lower one as the D1 and the other one will be D2. So this one D1, this one D2. So temperature change, delta D is equal to D1 alpha delta T. So delta T is equal to D1 delta D by D1 alpha. Delta D value see 0.9997, that is equal to 3. So this is 9 only, 0.0. So 3 into 10 to the power of minus 4 by D1 0.9997, you can take 1 only, and into alpha value, alpha 12 into 10 to the power of minus 6. So he asked temperature change only, not the final temperature, okay. So its simplification will give you temperature change, minimum rise in temperature only. So that is 25 degrees Celsius. Next, option A. A bimetallic strip is made up of aluminum and steel. On heating, the strip will remain straight, get twisted, bend with aluminum on concave side. Aluminum expand more than the steel. So, bend with steel on concave side. Aluminum more expansion. Heating, no? Concave side, who will be? Concave side, who will be? This is aluminum, this is steel. So, bends steel on concave side because aluminum expansion is more, steel expansion is less. So, concave side steel will be there. Yes, next. In a steady state, the temperature at the end of A and at B of a 20 centimeter long rod AB, the temperature at a point 9 centimeter equal to, okay, there is a rod of this much. Okay, it's 20 centimeter long, This is AB, maintained at 0 degrees Celsius, 100 degrees Celsius. Then temperature at 9 centimeter. At 9 centimeter, what will be the temperature? Is it a uniform rod? Okay. Then proportionality you can take. For 20 centimeters, 100 degrees is dropped. For 9, it's more than 50. More than 50, two options are there. 55 is there, 65 is there. No guessing. You need to go for the formula. Yeah. What is that? Here the rate of flow is equal to, not by taking like that, directly we have a derived formula. Why should we waste time? We can go for the derived formula. That is K1 theta 1 L2, K1 theta 1 L2 plus K2 theta 2 L1 by K1 L2 plus K2 L1 is junction temperature. That is equal to, here K is same only. So theta 1 L2 11 plus K2, K is same only, will cut. So K will cut. Theta 2 other temperature 0 into whatever will be 0 only, that is 9 by L1 plus L2 20. So answer will be 100 into 11 by 20, ding ding, 5 times, so 55. So we have derived formula. Why should we waste time? So 55. Two cylinders P and Q have same length and diameter and are made of different materials having thermal conductivities in the ratio K1 by K2 is equal to 2 by 3. These two cylinders are combined to make a cylinder. Okay, one point is at 100 degrees and the other one is 0 degrees. The temperature at the interface of P and Q is equal to, same interface, theta is equal to K1 L1, K1 theta 1, K1 theta 1 L2 plus K2 theta 2 L1 by K1 L2 plus K2 L1. So here he gave K1 by K2. So what you need to do is, you take common of K2 in the numerator and denominator and you can cancel. So it will become like this, K1 by K2 into theta 1 L2 plus K2 taken common. So you no need to write, K2 taken common. K2 taken common. So theta 2 L1 by, again K1 by K2 into L2 plus L1. Okay. So on substituting the things, same length, even length also can cancel, ding ding, ding ding, because length is same, diameter also same, area is also same, made of different materials. Okay. So theta equal to K1 by K2, 2 by 3 into theta 1 is 100 degrees Celsius plus theta 2 anyway will become 0 by, this is 2 by 3 plus 1, plus 1, that must be great. Now it is 2 by 3 into 100 by, this is 5 by 3, okay, 3 gets cancelled, 22s are 40 degrees. Ding 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 ding. Yes, some formula you need to. A perfect black body, the absorption quotient is 1. For perfect black body, everything maximum things only. Next, a calorimeter contains 0.5 kg of water. Calorimeter contains mass of water is equal to 0.5 kg at temperature theta 1 equal to 30 degrees Celsius. when 0.3 kg of water at 60 degrees Celsius is added to it, another water M2W is equal to 0.3 kg. 0.3 kg is added at theta 2 equal to 60 degrees Celsius. The resulting temperature to be 40 degrees Celsius. Water equivalent of calorimeter is how much? Water equivalent of calorimeter, mass of calorimeter is equal to how much in terms of water only we have to tell. First, if we can find out that one, then we can go for equivalent. So we have methods of mixtures like this. That is, heat lost is equal to heat gain. Heat lost equal to heat gain. Heat lost is equal to M2 C2 delta theta 2. That is equal to heat gain is M1 C1 theta 1 plus M2 C2, that is calorimeter, M2 C2 delta theta of the calorimeter. So M2 is 300 gram because it is 1000 multiplication, so will come in grams. Into C value, water only know water, and MC will become water equivalent. So delta theta of hot body 60 to 40 20, that is equal to M1 500 gram into plus water equivalent into delta theta temperature 30 to 40 is 10 ding ding. So this is 2 3s are 600 is equal to 500 plus W, implies W is equal to 100 gram, 0.1 kg. Yeah. Two metallic spheres P and Q are made up of same material, have same smoothness, but the weight of P is 8 times that of Q. Two metallic spheres, so M of P, weight of P is 8 times that of Q, and the two are heated at the same temperature and left to cool. The rate of cooling is to that of, okay, rate of cooling, rate of radiations. People usually get confused. Rate of radiation, rate of cooling. These two things I want to once again mention. Rate of radiation is proportional to area. That means R square you can write. Okay. Rate of cooling is proportional to area by mass. So R square by R cube, that is equal to 1 by R. Rate of cooling is proportional to 1 by R. So these two must be considered very carefully, otherwise we are going to face a lot of problem. So here masses ratio is given MP by MQ. That means RP by RQ whole cube is equal to 8 by 1. Implies RP by RQ is equal to 2:1. Okay. Now rates of cooling, rate of cooling of Q to that of P. That means rate of cooling of Q to that of P. This is cooling. This is radiation. Okay. So rate of cooling to that of, this is P, that is equal to, that is inversely proportional. That means RP by RQ. See this one, this formula you have to use. So that is equal to 2:1 only. So 2 is the answer, C option. Next, solid copper sphere of density rho, specific heat C and radius R is initially at 200 Kelvin. Solid copper sphere of density rho, specific heat C, radius R, initially at theta 1 equal to 200 Kelvin. It is suspended inside a chamber whose walls are at 0 degrees Celsius. Theta 2 is equal to 0 degrees Celsius. The time required for the temperature of the sphere to drop, temperature of the sphere 100 Kelvin to drop, okay, time T is equal to how much? So we will use Stephen's law formula, that is rate of heat transfer is equal to, it's a falling time only, no? So we can go for the complete derivation part, that is Stephen's law we have to use, rate of cooling also we have to use, solid copper sphere of density, so rate of cooling also we need to use. So both we need to use. They are rate of radiation dq by dt is equal to sigma a e into t to the power of 4 minus t naught to the power of 4. And this one is, I can write mc delta theta by time taken. So I want time taken. Time t is equal to, mass is the volume into density into c into temperature difference by sigma a e t to the power of 4 minus t naught to the power of 4. These things we need to substitute. So substitution is as follows. 4/3 pi r cube rho c delta theta 100 by sigma a 4 pi r square into e. E value they didn't give. Okay, e value close to blackboard I can take, and 200 to the power of 4 minus 0. So 4 pi gets cancelled, blah blah blah, and doing all these r cube. So 2 to the power of 4, 2 2s are 4, 2s are 16, 16 3s are 48, 1 by 48, 1 by 48, two options are there. R rho c, R will be R rho c, okay, R rho c by sigma. So option R rho c by sigma 2, okay, 48 in denominator, only one option is there, B option only, R rho c by sigma, that is B only, yes. Next, steam at 100 degrees Celsius is passed into 1 kg of water contained. See, this type of problems you need to draw a graph. Now, steam at 100 degrees Celsius is passed. Water of 1 kg contained in a calorimeter at 90 degrees Celsius. Minus 10 water and steam. You need to think it like this. So water at 90 degrees, here is the initial task. This is 0 degrees, this is 100 degrees, and calorimeter is increased to 90 degrees. Wait, passed into 1 kg of water contained in a calorimeter at 90 degrees Celsius till the temperature of water and calorimeter is increased to 90 degrees Celsius. The mass of the steam condensed is nearly 0.1 kg. Okay, specific heat of water is given and latent heat of vaporization. What we have to find? The mass of the steam. Okay, that means initial final temperatures he gave same. No, it should be different. So I need to change the question terminology. It's actually 9 degrees to 90 degrees. Then only we can do it. Calorimeter is at 9 degrees. Here point I can put so that it will be done. Yeah. So initially it's at 9 degrees, 90 degrees. So calorimeter and water raised through how much? 9 degrees to 90 degrees. See, heat absorbed is equal to mc delta theta, heat absorbed is equal to heat lost, steam condensed, steam cooled. So m condensed, ml plus m cooled, mc delta theta for heat absorbed, heat liberated. M value 1 kg, and that one also, okay, kg only, grams in the answer. So 1000 into C value, specific heat of water is 1 into grams is better, and water equivalent of calorimeter is 0.1 kg. Oh, you have to 0.1 kg means 100 grams, that must be added here. And theta A, how much? 9 degrees to 90 degrees. 9 degrees to 90 degrees. This is 9 degrees. 9 to 90 minus 9 degrees is equal to m. I have to find out. L is 540 plus 1 into temperature difference. This is only 100 to 90 only. So in cooling, right, that's why. So capital M is equal to, this is 110 into 81 by 540 into 10. 540, okay, not into 10, this is plus 550. So nice numbers. 110 will go 5 times. So M is equal to how many times? 16 roughly. 16 grams. So here it is 1100 into 81 and M is equal to. So this is 1100 5 times and here 10 times. So 162 gram. 162 gram is nearest number maybe. Okay. Next. 3 uniform thin aluminum rods, each of length K3, each of length 2 meter, form an equilateral triangle PQR as shown in the figure. The midpoint of the rod PQ is at the origin of the coordinate system. If the temperature of the system of rods increased by 50 degrees, the increase in y coordinate of the center of mass of the system of the rod is quotient of linear volume expansion of the aluminum is given. This is cheating. Quotient of volume expansion gamma is equal to 3 alpha actually. So gamma by 3 will give you alpha. Alpha equal to by 3 I have to go for. So 4 into root 3 into by 3. By 3 will be 4 root 3 into 10 to the power of minus 6 per Kelvin. Okay. So center of mass is elevated by how much? He is asking that. Center of mass elevation we need to find out. See, two cases we have to consider. Suppose the first case, its center of mass will be here. Y coordinates only we can consider. Center of mass will be here. How much? What is the Y value? That is, this is at origin only. Oh, yeah, this one will be here and this one will be here. So this one will be here. So 1m is at 0. This is 0 only, no? 0 comma 0. So 0 only. Y values only we are writing. Another m is at this height. At what height it will be? That we need to find out. That is how. This is half of the length L by 2. And this angle is 60 degrees. 60 degrees. Then this will be how much? See, I repeat. This is L by 2. Length is given at 2 meters. So it will be 1 meter. And this is 60 degrees. 60 degrees. Then this will be, or this will be 30 degrees. Then this will be cos 30. You can take cos 30. 1 cos 30. That is root 3 by 2. So this is root 3 by 2. The other one is also root 3 by 2 only. Another m also at root 3 by 2 only. So initial center of mass location y initial is equal to m1y1 plus m2y2 plus m3y3, m1y1 plus m2y2 plus m3y3 by m1 plus m2 plus m3, 3m. So this gets cancelled. So that is to root 3 by 2 plus root 3 by 2. Now final length will not be 2 meters. That final length is equal to L2 is equal to, on heating what happens? L2 equal to L1 of 1 plus alpha delta T or delta theta. L2 is 2 meter, okay, 2 meter, 1 plus alpha value 4 root 3 into delta theta is 10 power 4 root 3 10 power minus 6 into delta theta. How many degrees it has raised? 50 degrees. 50 degrees Celsius. 200 means 2 root 3 into 10 to the power of, this is 2 into 1 plus 2 root 3 into 10 to the power of minus 4. And it is simplified as, so initial center of mass we got at a height of 1 by root 3. Now change of center of mass in y direction only, that is equal to L, normally change is equal to delta L equal to L alpha delta theta. You can directly use that. Change equal to L is 1 by root 3, alpha is 4 root 3 into 10 to the power of minus 6 into delta theta 50 are 50. So that is equal to 5 4s are 200. Root 3 will go. So 2 into 10 to the power of minus 6. 200 is there. So 200 is there. It will be 2 into 10 to the power of minus 4 meter. That means 0.2 mm. It's in 0.2 mm. Next. It's easy. The ratio of energies of emitted radiation by a black body at T1 is equal to 600 Kelvin and T2 is equal to 933 Kelvin. Surrounding temperature T0 is equal to 300 Kelvin. Okay. Ratio of energies emitted. Okay, he is expecting ratio of energies emitted. So E is proportional to T for 4 minus T0 to the power of 4. So ratio will be E1 by E2 is equal to 600 power 4 minus 300 power 4 by 933 power 4 minus 300 power 4. So hundreds will go, but this is 933. Will it be 933? Maybe 900, I feel so. Let me take 900 and do. I got a doubt. So here 300 power 4 can be cancelled. So 2 power 4 minus 1 by, this is 3 power 4 minus 1. 15 by, this is 81. 81 minus 1 is 80. That means 5 table will go 3 times, 5 table will go 16. 3 by 16. Yeah, this is not 933, this is 900 only. Yeah, 900. Okay, yes, next. Let me mark it, otherwise I'll forget. Next. Which of the following curves represent the variation of quotient of volume of an ideal gas at constant pressure? At constant pressure, volume variation. At constant pressure, volume variation we need to find out. We'll use these equations. PV is equal to nRT. P delta V as pressure is constant. nR delta T. So delta V by delta T is equal to nR by P. And we have PV equal to nRT. So 1 by T is equal to, or I want V is equal to nRT by P. V is equal to nRT by P. So dividing this one also, then I want this one, delta V by V delta T is equal to, that means nR by P divided by nRT by P. I have to write P gets cancelled, nR will cancel, 1 by T will come. So this is only alpha. So alpha is proportional to 1 by T. Alpha proportional to 1 by T means it should pass through origin and a straight line. So this one will. So by definition only, definition you need to follow, that's it. B. Next. Cup of tea cools from 65.5 to 62.5 in 1 minute at the room temperature. How long will it take to cool from 46.5 to 40.5 in the same room? Okay, this is T equal to how much? Room temperature is missing, I think. I need to find it up. I have taken the room temperature value. Now we can go. 22.5 degrees. So theta naught is equal to 22.5 degrees Celsius. See, oh, what happened? Yes. Now, rate of cooling. Theta 1 minus theta 2 by T is equal to some constant into, of course, negative sign and all I am not taking. Theta 1 plus theta 2 by 2 minus theta naught. Writing this, 65.5 minus 62.5 by T value First one 1 minute, 1 minute, 1 minute. Answer will come in minutes only, is equal to K into 65.5 plus 62.5 by 2 minus 22.5. This is equation 1. Let me write equation 2 also. 46.5 minus 40.5 by how much time? T time I have to find, and that is equal to K into 46.5 plus 40.5 by 2 minus 22.5. This is second equation. So dividing 1 with 2, the T value is equal to how much time will it come? It will come as 4 minutes, right? 4 minutes. Yes, next. A pan filled with a hot food cools from 94 degrees Celsius to 8 degrees Celsius, 94 degrees Celsius to 8 degrees Celsius in 2 minutes. When the room temperature is 20 degrees Celsius, theta naught is equal to 20 degrees Celsius. How long will it take? 74 degrees Celsius to 10.66, I think it is 10.66 degrees Celsius or 10.6. Let us write the same expression. I changed the necessary things. Now the same expression we can use. Rate of cooling. Theta 1 minus theta 2 by T is equal to some constant into theta 1 plus theta 2 by 2 minus theta naught. So using this equation, we can have 94 minus 8 by 2 minutes is equal to K into 94 plus 8 by 2 minus theta naught is 20, representation 1, and 74 minus 66 by 2 by 2 oh, this is 2 minutes. Okay, here time I don't know, no, this time I have to find it up. So that is equal to T equal to K into 74 plus 66 by 2 minus the room temperature is 20. So this is equation 2. On solving equation 1 by equation 2 implies we will get T equal to 2.8 minutes roughly, right? Isn't it? Yes. Next. 1 gram of ice is mixed with 1 gram of steam. At thermal equilibrium, the temperature of the mixture is 1 gram of ice is mixed with 1 gram of steam. 1 gram of steam will produce 540 calories, 540 calories of heat. Out of that, 80 calories is absorbed by ice. Then what happens? 0. This is 40. Okay, 540. I will do like this, somewhat different way. 1 gram of steam, 1 gram of steam comes to suppose 0 degrees, Celsius. How much heat will be liberated? Steam conversion 540, coming to 0 degrees 100, so total will be 640. Now 1 gram of ice, first ice melts, so automatically it absorbs 80 calories. So minus 80 will be, it will be 0, 40 and another 40, 560, 560. So 560 calories is left. 560 calories is left. And this 560 calories should be shared by the 2 grams. 560 calories should be shared by 2 grams. So 560 calories by 2 grams will give you some 280 degrees Celsius. 280 degrees Celsius means mean to say 280 calories is with it. For every calorie 1 degree will be raised. So it can't evaporate, because for evaporation how much is needed? For evaporation 540 calories is needed. This is not that much. So it will come to 100 degrees Celsius and will stay back. So fractional steam only will be condensed. Remaining will be in the steam form, actual in practice. So 100 degrees Celsius is the answer. Yes. Next. On the temperature scale X, the boiling point of water is 55. The freezing point is 15. And the assume that x is a linear scale, equivalent temperature corresponding to -5 degrees x in Fahrenheit. So conversion is LFP, LFP minus U. Okay, conversion is measured reading minus LFP by UFP minus LFP is equal to constant. So using this, how much you want to change? 95 minus 95 minus LFP is minus 15, not plus 15, minus 15 by UFP is 65 and minus 15 is equal to Fahrenheit. We have to find F minus 32 by 212 minus 32. So it will be minus 95 plus 15 by 65 plus 15, 80 is equal to F minus 32 by 180. So F is equal to, how much will come? I don't want to waste, minus 148 degrees Fahrenheit. Next. The two ends of the rod of length L and uniform cross section area A are kept at two temperatures T1 and T2. Okay, the rate of heat transfer dq by dt of the rod in steady state is given by Ka delta theta by L. So that is option C. Yes. Next. Two bodies A and B are placed in an evacuated vessel maintaining temperature 27 degrees Celsius. The temperature of A 327 and to that of 227. The ratio of heat loss from A and B, heat loss only, not rate of cooling, heat loss only. Heat loss is E1 by E2 is equal to, first one is 327 degrees Celsius. So it must be converted into Kelvin. So plus 273. Power 4 minus 300. This is plus 273 will be 300 Kelvin. Power 4 by this one also 227 plus 273 500 power 4 minus 300 power 4. So this will be 400 600 to the power 4 minus 300 to the power 4 by 500 to the power of 4 minus 300 to the power of 4. So somewhat bigger calculation. Is it 500 or 600? If that is 600, then this should be 500 only. So calculation must be done patiently, right? So on doing patientic calculation, we'll get hardly 2:1, right? So option 1. Practice more problems. And some chapters like mechanical properties of solids and this thermal properties needs some calculation ability. You need to be patientic enough at that stages. Then only scoring will be improved. Keep on practicing and we'll discuss in another chapter. We'll meet again. Bye.